In this course, we are interested in linear state space models. They consist of two equations. The first equation is a linear differential equation x dot equal to ax plus bu, and this is called the state equation. The second equation is a linear algebraic equation y equal to cx plus du, which is called the output equation. Here, x is a vector in Rn called the state of the system, u is in Rm, it is the input to the system, y belongs to Rp, and it is a system output. The matrix A is an n cross n matrix called the state matrix. B is an n cross m matrix called the input or control matrix. C is a p cross n matrix called the output or observation matrix. And D is a p cross m matrix called the feed through matrix. Here n, m and p are some integers. The objective of this course is as follows. Using state space models of linear control systems, we want to study control theoretic aspects such as stability, controllability, observability, controller design, and observer design. So we take linear control systems, then we model them as state space models, and then using these state space models, we want to study control theoretic aspects of the linear control system. Now, the dynamics of many engineering systems can be captured reasonably well using a linear model. So let us now look at two simple dynamical systems and find their state space models. So we'll look at two examples now. The first example is the spring mass system shown here. Here K is a positive constant called the spring constant. M is the mass of the block. F is the external force acting on the block, and we will treat this as the input to our system. L is the rest position of the block when the spring is neither stretched nor compressed. And Z is the displacement of the block from the rest position. So this is our notation. Now the force exerted by the spring on the block is given by the Hooke's law, and the expression for this force is minus kz. So from Newton's law of motion, we get that mz double dot of t is equal to f of t minus kz of t. This is mass into acceleration, and this is the net force acting on the block. F is the external force and minus kz is the force due to the spring. We can equivalently write this equation as mz double dot of t plus kz of t is equal to f of t. This is a linear differential equation which governs the dynamics of our spring mass system. To write this equation in the state space form, let us define x1 equal to z, x2 equal to z dot, x to be the vector x1, x2, and u is equal to f. Then x1 dot is nothing but z dot, which is x2, and x2 dot is z double dot, which using this expression, the linear differential equation, we get x2 dot is equal to minus k by m x1 of t plus 1 by m u of t. Now I can write this equation in matrix form as follows. X dot of t is 0 1 minus k by m 0 x of t plus 0 1 by m u of t. Let me label this equation as 1. This equation is the state equation for the spring mass system. X is a two-dimensional vector which is a state. This 2 cross 2 matrix is the state matrix A, and this 2 cross 1 matrix is the input matrix B. Suppose we are measuring the position of the block. Suppose we measure Z. Then the output equation becomes y of t is 1 0 applied to x of t. X of t is x1 x2, so 1 0 applied to it gives me x1 of t, which is exactly z of t. So this is my output equation, and this is the C matrix, which is a 1 cross 2 matrix. Now the state equations are not necessarily unique for a given dynamical system. For instance, suppose I define x1 to be, I define x1 equal to z, x2 equal to z plus z dot, x to be the vector x1 x2 and u to be equal to f. Then using the procedure that we followed to derive the state equation 1, we get the state equation to be x dot of t is equal to minus 1 1 minus k by m minus 1 1 x of t plus 0 1 by m u of t. Let me label this equation as 2. See, both 1 and 2, they describe the state dynamics of my spring mass system, but in different coordinate systems. Okay, so both 1 and 2 describe the state dynamics, but in different coordinate systems. Now, of course, in these new coordinates, the output equation continues to be 1 0 x of t. This remains the same because we are still measuring z. Now that we have a state space model, what can be a control problem of interest? Suppose f is 0, that is, there is no external force acting on the block. The initial position of the block z of 0 is not equal to 0, that is, I have moved the block away from the rest position, and z dot of 0, the initial velocity of the block is 0. Then if I look at this differential equation here, which is governing the dynamics, the solution to this differential equation z of t is given by this formula. Z of t is z naught cos root k by m t for all t greater than or equal to 0. So if there is no external force with these initial conditions, the block is going to oscillate. It will not settle down at its rest position. So a possible control problem is find a formula for f such that for any initial state, any initial position z of 0 and any initial velocity z dot of 0, we get z of t converging to 0 and z dot of t converging to 0 as t goes to infinity. So I need to find a formula for f. So if you put that formula for f in this linear differential equation, then for any initial condition, that is any initial position and any initial velocity of the initial of the differential equation, z of t and z dot of t should converge to 0. We will find such a formula using the state space model in this course. In the next video, I will present another example for deriving the state space model.